Hello, and welcome back to part 2 of lesson 6. In this video, we're going to be talking about more array functions, particularly as they're related to the multidimensional arrays that we talked about in part 1. So every object that we've learned about so far that has had a dimension has had the dimension of length, right? So lists have had length, strings have had length, one-dimensional arrays have had length, and for all of those objects, the length has been the only dimension. For multi-dimensional arrays, they have more than just a length. So they do have a length, but they have other dimensions as well, which means that when we're looking at them, we have to think about some of the other characteristics than just the length. Here we have a few examples of arrays. We have a one-dimensional array D1, and that's np.array 1, 2, 3, 4. Simple, straightforward, one-dimensional array. We have D2, which is our two-dimensional array, and that's going to be 2 rows and 4 columns, which is 1, 2, 3, 4, 5, 6, 7, 8. And then we have D3, our three-dimensional array, which is going to have 3 layers, each with 2 rows and 4 columns. All of these objects do have a length, and they do have that length dimension. So when we do the length function on them, we get answers, right? So we have length of D1, and that's going to be the same as just getting the same the number of items in there. So it's 1, 2, 3, 4, and that gives us 4 items. If we do length of D2, however, it doesn't give us the number of items in that array. It gives us the number of items in the outer list, right? So the outer list, when we're creating this, remember, the brackets are here, and you have these 2 inner lists. So 1, 2, and that length will then give us 2. And what that's really giving us is the number of rows in our two-dimensional array. For a three-dimensional array, it does something similar. It gives us the number of items in the outer list, right? So outer list and outer list. In this array object here, we have 3 items. So that's going to give us a 3. What that really is telling us is how many layers are in our three-dimensional array. So as you can see, it does give us answers, and these things do have length, but it doesn't tell us the full story. It doesn't tell us any of the other objects or how many total items there are. To do that, we would have to look at the attributes of these multidimensional arrays. And one attribute is, in fact, the size. So that gives us the total number of items in the array. This is very similar to doing the length function on a one-dimensional object, and it should produce the same answer if you do it on a one-dimensional object. As you can see here, we have d1.size, and that gives us 4 because there are still just 1, 2, 3, 4 objects inside of this array. Now, when you do it on d2.size, our two-dimensional array, it gives us an 8, which is just the number of rows times the number of columns. And that's the total number of objects inside of this array. And then finally, for D3, so D3.size, we have the number of layers times the number of rows times the number of columns, which in this case is 3 times 2 times 4, and that gets us 24 total number of items. Now notice that there are no parentheses at the end of this statement, and that's because it's not a function, it's an attribute, right? So we can't change it in this way. We're really just investigating deeper into what these multidimensional arrays or single-dimensional array look like. Another attribute to look at is the number of dimensions. So ndim here gives the number of dimensions in an array. So when you do d1.ndim, because this is our one-dimensional array, we're going to get a 1. d2.ndim, this is our two-dimensional array, and we get a 2. And d3.ndim, our three-dimensional array, gives us a 3. This can be helpful for knowing sort of how you want to index or slice, but it really doesn't tell us much about, how these dimensions are shaped or how many objects are inside. So it just tells us a little bit of information. The final attribute I want to talk about is the most used, and that's probably because it gives us the most information, and it gives the number of items in each dimension of an array. So when you do d2.shape, our two-dimensional array, it's going to give you a tuple here, and it's going to give you a 2 and a 4. So it's going to be the number of rows and the number of columns. Same thing with our d3. So d3.shape is going to give you the number of layers, the number of rows, and then the number of columns. Now d1.shape is also going to give you a tuple, and that's why it gives us this sort of weird format of a number, a comma, and then a blank, because tuples don't like to have lonely numbers. They sort of just put one in there and then give you a blank at the end. So when you see formats like this, just know that it's a one-dimensional array. So now that we know sort of how to find out about our arrays, we can also change the shape of our arrays in order to make it easier to work with them, right? So we have our same arrays here, and we're going to use the reshape function. So this changes the shape of an array into a given shape. Now this given shape is something that you're going to put into the function. Notice it is a function because it has its parentheses here. And you're going to tell it the number of rows and the columns that you want it to change into. So here we have our one-dimensional array, and we're going to change it into a two-dimensional array. So we have d1.reshape, and I say let's put in 2 rows and 2 columns. And notice that I give that in a tuple inside of this function. And when we print it out, you can see we have our 2 rows and our 2 columns rather than the original just one-dimensional 1, 2, 3, 4. We can also change our D3 into a D2, our 3-dimensional array into a 2-dimensional array. But to do that, we just say D3.reshape 2, 12. Notice again, that is a tuple. And that's just saying I want 2 rows and 12 columns. So 2 rows here and 12 columns going along. If you try to put in a number of rows and a number of columns that doesn't match the number of total elements that you have, you're going to get an error. So you can use that size attribute and shape attribute in order to really fine-tune what the rows and columns you want in the end. Another way to change the shape of your NumPy array is to flatten it. You just kind of squish it down, it ignores all the rows and columns, and it just spits out a single one-dimensional array. So here, for our example, we have our 3-dimensional array, D3. You can see it has all this structure with the layers and the columns and the rows. And then we say D3.flatten, and it just squishes it down into a single one-dimensional array, 1 to 24 there. But the final way to change the shape of your NumPy array is actually to transpose it. What that does is it actually sort of rotates the axes of an array in order to change the number of rows and columns without changing your values inside. Right? So here we have our example of our 2-dimensional array D2, and we say D2.transpose. You notice the original is 2 rows and 4 columns, and you can see that the final transposed array is 4 rows and 2 columns. Right? So it basically just takes that upper column and that lower column, and it stands them up right next to each other in order to give it that different shape. So when you change the shape, you can actually continue to do sort of more arithmetic operations with the arrays. So you can, add and subtract and multiply and do all of these arithmetic operators with multidimensional arrays, just the same as you can with one-dimensional arrays. You can also do it with numbers to each array, and it performs these computations element-wise, just the same way as in one-dimensional arrays. If you recall from the previous lesson, element-wise operations require arrays to be the same dimensions, right? You can't add something with 3 dimensions to something with 5 dimensions. It doesn't work. Multidimensional arrays work the same way, except when you're adding or performing some kind of arithmetic operation, you can have them have slightly different dimensions, but the dimension which you're adding or performing this operation on has to be the same. So what I mean by that is sort of the broadcasting of our arrays. So here in our nice little picture, we have a few different array boxes. So here we have an array with 0s, 10s, 20s, and 30s. And we have another array of 0s in columns, 1s in columns, and 2s in columns. So when we add those together, these are the same size. It's going to add each object into its same index values there. So it's going to end up with something that looks like this. Now, if you have an array that looks like this, and then you add an array with just 1 row to it, it will actually broadcast that row in order to add it to all of the other rows from the original array. So here, this example, we have our 0, 10, 20, 30, and here we just have a 0, 1, 2. And what it does is it sort of fills that out to look the same as it was up here. So you get the same answer, actually. And a little bit more complicated, if you have just a single column and just a single row, it will actually fill in all of those rows and columns in order to give you the same size thing. So broadcasting is kind of neat, but it can get a little bit tricky making sure that things are matching up together. So in our example here, we have our D2, our 2-dimensional array, and our D1, 1-dimensional array. You'll notice that they are different shapes here. This one has 2 rows, this one has 1 row. But whenever we add D2 plus D1, it's going to take every element in this D1, and it's going to add them to each of the rows in D2. So it's going to be 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6, 4 plus 4 is 8, and then it's going to take this row again and add it to the next row. So it's going to go 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. So you can also combine your NumPy arrays. Instead of adding them or doing arithmetic with them, you can combine them into a single NumPy array in order to make things sort of easier to work with or save it as one big array. So one way to do that is to do vstack, which stacks the array on top of each other vertically, right? So here we have D1 and D2, and then we say np.vstack D1 comma D2. Notice I give this as a tuple here. So what that does is it takes D1 and it just puts it right on top of D2, and that is now a two-dimensional array with 3 rows instead of just 2 rows. Similarly, there's hstack, which stacks arrays horizontally. So I create this sort of D1 vertical, which is this vertical 1, 2, 3, 4, rather than horizontal. So then I say D2 transpose, which then puts these sort of vertical, it puts the same number of rows as our D1 vertical here. And when I say D1 vertical and D2 transpose, and I do our hstack here, it puts it right on the end. Just like in one-dimensional arrays as well, you can have mathematical reductions. So that's using these NumPy functions sum, mean, median, max, min, and standard deviation in order to get just one number to describe our arrays. You can do the same thing with multidimensional arrays as you can with one-dimensional arrays, but a lot of times you're going to have to add an extra argument here of an axis, right? So it's going to tell you what axis you're going to be doing this function on. So here we have our sample array 11, 22, 33, 44, and then another row 5, 4, 3, 2. Right, and the axis 1 is going to be along the rows, and then axis 0 is going to be along the columns. So here, if we have np.sum of x, our sample array here, along axis 0, it's going to be along the columns, right? So it's going to sum on the columns. So 11 plus 5, 16, 22 plus 4, 26, 33 plus 3, 36, 44 plus 2 is 46. So that's what the answer to that one is going to be. Similarly, if we do a mean and we say x axis 1, that means it's going to do it along the rows. So it's going to do the mean of each of the rows, which in this case, 11 plus 22 plus 33 plus 44, all divided by 4, is 27.5. And 5 plus 4 plus 3 plus 2 divided by 4 is going to be 3.5. So that's going to be our solution to the mean of the rows. Now, if you wanted to do the mean of the columns, you would just do a 0 here instead. Same thing with the median, x axis equals 0. So we're going to be doing it in the columns, right? So the median of each of these columns is 8, 13, 18, and 23. Now you can do it without giving these axis arguments. And what that does is actually just takes this function and does it for all the numbers in there. So we have np.max of x, and that's just going to be 44 because that's the biggest number in all of these here. Another example of doing it along the rows here is np.min of x, comma axis equals 1. So it's along the rows. And the minimum of each of those rows is 11 and 2. And finally, we have our standard deviation, which we did for all of the numbers here, and that's going to be 14.84. So if you don't want to do it along these axes, you don't have to. You can do it with all of the numbers in there. But it can be very helpful to do these means or sums across axes. Finally, we also learned about how to create new arrays of single dimension arrays, and we can also do this for multidimensional arrays using a few of these same functions here. So we have zeros, ones, and full. So instead of giving it just one number, instead we give it a tuple here. So we want 4 rows and 3 columns, and it gives us 4 rows of zeros with 3 columns. Same thing, if you want to give it a tuple and you have a one-dimensional array, it does give you that one-dimensional array if you just leave that blank, and if you remember that format from before. And then if you want to do a 3-dimensional array here for a full, you give it, again, that tuple with 2. So it's going to give you 2 layers, 3 rows, and 4 columns for each. So 2 layers, 3 rows, and 4 columns, all filled with 2's. So you can create multidimensional arrays just as easily as single dimension arrays. That brings us to the end of our more array functions. This one was a little bit longer, and the next couple should be a little bit shorter. So feel free to take a break, and I will see you back here soon.